I'm going to talk, of course, of polynomial identities, but my focus is going to be on differential polynomial identities. Differential. The word differential is a word that is really connected to the concept that we know since, I guess, high school, but for sure since the first courses of calculus, of derivative. In fact, if we consider the usual derivative, we know that derivatives satisfy some rules. There is that are the sum rule and the constant factor rule. Also, for the product, the usual derivative, we know that satisfy the Leibniz rule. So this tell us that sorry, I don't know, it's not going on. I have a problem with connection, internet connection. I'm sorry. Okay, now it's working. So we know that the derivatives satisfy all these rules that tell us basically that the differential operators is a linear operation, is a linear map that satisfies the Leibniz rule. Then this concept can be defined in a more general way for algebras. And in fact, if we consider a field, in our case, it's going to be a field of characteristic 0, but it can be defined on any field and any algebra over F, then we can define a derivation of A as a linear map that satisfies the Leibniz rule. An easy example, in case, for example, A is associative, then an example of derivation are the so-called inner derivation, that are the derivation induced by a fixed element of A, and they are acting in this way. Basically, are the commutator, by A. A really interesting, important property of derivation is that if we consider the set of all derivation of an algebra A, then this set has a really strong structure. In fact, it is a Lie algebra, but with respect to this separation, where in here we have the composition of derivation. We have to be careful because composition of derivation is not in general a derivation. However, when we do the commutator, we get always a derivation. So the objective now is how to find objects that have a good, we have to find a good definition of action by derivation on an algebra, because we want to study objects that we call algebras with derivation. So they have this action. But before, I'll give you an example of derivation. So if we consider the algebra of 2 times 2 upper triangular matrices, then Coelho and Polsino in 1993, they proved that any derivation UT2 is inner. They actually proved that any derivation of UTK over a field is inner. In particular, for the case of UT2, we have, if we consider these two derivation, inner derivation, epsilon, that is the derivation induced by E11, and delta, that is the derivation induced by E12, then these two derivations are actually a basis for the Lie algebra of derivation of UT2, and the product of these two derivation is this one. So delta, the commutator of delta epsilon is equal to delta. So now, as I told before, the product of two derivation is not a derivation. So when we define an object with an action of derivation, we have this problem that we have to deal with composition also of derivation that is not in general derivation. To avoid this problem, we are going to consider the universal enveloping algebra of our Lie algebra. So we fix a Lie algebra F, and we consider universal enveloping algebra of L. Of course, this is the universal, this object, the universal enveloping algebra of L, always exists, and is unique up to isomorphism. Then we have this object is universal in the meaning of a universal property. Okay, so it satisfies the universal property. So we have a really strong property that comes from the theorem of Pokareb-Birkhoff width, that if we fix a basis, our order basis of L, then the UL, our enveloping universal algebra, that is an associative algebra with unit, has as basis this one. So basically is product of derivation where the order matters, so our ordered monomials in the elements of L. And this is really strong. It's really a useful property. So whenever we have a Lie algebra and a basis, an order basis, we can find the basis of the universal enveloping algebra. Two examples. The first, if L is the trivial Lie algebra, is the zero Lie algebra. Then the universal enveloping algebra, it's easy to see from the Pokareb-Birkhoff width theorem, is just generated by the unit. So the unit is the empty word, okay? And so is isomorphic to the field. This is the only case in which the universal enveloping algebra is actually finite dimensional. In fact, if we consider, for example, a one-dimensional Lie algebra generated by one element, then the universal enveloping algebra it's a linear combination of elements of words of element delta to k, so of this type, and then it's isomorphic to the ring, to the algebra of the ring polynomial, of the polynomial. Okay, so now we are ready to define the main object on my talk, that is the algebra with derivation. So from now on, A is going to be an associative algebra, and L is going to be a Lie algebra over F, acting on A by derivation. So acting on A by derivation means that there exists an homomorphism of Lie algebra from L to the derivation algebra of A. And then, since the universal enveloping algebra is a universal algebra, we can extend naturally this homomorphism to an homomorphism of associative algebra. And in particular, since we want a right action, we are gonna send it to the, if endomorphism, we are gonna send it to the algebra of endomorphism of A in the opposite. So we are going to consider the endomorphism acting on the right. Okay. So in this way, A become a right UL module, and we call it algebra with derivation or L algebra. Okay. So we are considering not just the action of L, but we are actually considering the action of all UL. So how works this action? From the Pokareb-Birkhoff width theorem, we have then, if we are acting on A by an element of the basis of UL, then this action is actually acting first by the first element of the basis, then second, and so on. Okay, so now let's see an example. When we have a trivial action. So we are going to consider an associative algebra, an Lie algebra, and then we consider the trivial action by derivation. One means that L is sent to the zero Lie subalgebra of the derivation algebra. Okay, and then of course we can extend this action to the whole to the action of UL, and the point is to understand which are the interesting elements in our algebra with the derivation. We want to understand which is the images of UL in the endomorphism. Why? Because UL, we know, is in general it's an infinite dimensional algebra, but so there are lots of elements, but in between them, which one are really interesting? So they are acting not trivially. So to understand which is the images of UL through this homomorphism, we consider the kernel. That is, in this case, the kernel of the homomorphism phi0 is, of course, the two-sided EL generated by any element of L. So the image of UL that is clearly isomorphic by the theorem, the homomorphism theorem, this homomorphism theorem to UL module the kernel, it's isomorphic actually to the field. So the only interesting element, the only interesting action, it's the one of the unit. So basically, we have just the normal associative algebra. So any associative algebra can be regarded as L algebra, where L acts trivially on it. So if we consider UT2 with a trivial action, this is in particular an L algebra. Okay, a less trivial example. If we consider now UT2, but now we are considering an action by derivation given by the inner derivation induced by the element E11. And then we consider the universal enveloping algebra of the algebra, of the one-dimensional algebra generated by epsilon. And then, again, we want to understand which is the action of UL on U. So we want to understand which is the images of UL inside the endomorphism algebra of UT2. Let's see how epsilon act on a matrices of UT2. Of course, epsilon do this job, and so basically send all matrices, any matrices, to the corner. So if I apply another time epsilon, and I do epsilon square, I'm gonna obtain again just the corner, because epsilon fixed the corner actually. So this what tell us. This actually tells us that epsilon square minus epsilon is an element of the kernel, and more, we know that actually the kernel of this homomorphism phi is the two-sided EL generated by this element, epsilon square minus epsilon. So basically, the only two, the really interesting action in this case, so the elements that are really interesting in the action are just the unit and the derivation epsilon, because all the other can be reduced to the action of epsilon or are trivial. Okay, so finally we can define the differential polynomials. To define the differential polynomials, we need a free object that take into consideration that we have this structure of derivation. We have derivation also. So we consider the algebra L, its universal enveloping algebra with easy basis. And then we consider sets of countable non-commutative variables. And then we consider the free associative algebra over F with generators xj to di, where x is an element of our set X, and di is an element of the basis of UL. Then this is clearly a vector spaces, and a basis of this free algebra is, of course, consisting in all these kind of words. So basically, are polynomial in which in an exponent of the variable we have elements of UL, and the multiplication is just the juxtaposition. This free associative algebra is actually, it has actually a structure of L algebra by defining in a formal way this action. So we are imposing that L acts by derivation on our free algebra, and this free associative algebra satisfies this universal property. That means that is actually a free associative L algebra, okay? And we call its element differential polynomials. So a differential identities, if A is an L algebra, a differential identity of A is a differential polynomial that satisfy, go to zero whenever we evaluated the variable in any element of our algebra. So let's fix the notation that whenever I have the unit of UL acting, I omit it. so it's just a variable. And then an example of differential identities is this one. As in the first talk, Professor Plowman say, UT2 for UTK, but in particular for UT2, as ordinary polynomial, as ordinary polynomial identities. And then, of course, this is in particular a differential identities of UT2. Okay, a less trivial example. So we are going to consider again UT2 epsilon, where our epsilon is, so it's UT2 with the action of L, where L is the one-dimensional Lie algebra generated by the derivation induced by E11. Already we know the kernel of the action of UL, etc. So first of all, we have to notice that if we take an element in the kernel, then this means that if we apply this element of the kernel in any matrices of UT2, then we get 0, is the kernel of the action, right? So this say in particular that this one is a differential identities of UT2 epsilon. Also, we know what? That the commutator of any two upper triangular matrices is a matrix of the type E12. And also that by the action of epsilon, epsilon fixes exactly the element E12. So if we apply epsilon to a matrix of the type E12, it's going to fix it. Then this means, in terms of polynomial identities, that this one is a differential identities of UT2 epsilon. That is, that epsilon fixes the commutator. Okay, the main question, the classical question in theory of polynomial identities, is find the, in this case, differential identities of a given algebra. Then, as usual, we consider the set of all differential identities. This set has a structure, a really strong structure, is a T ideal, TL ideal, so it's invariant under L endomorphism of the free L algebra. And any TL ideal is of this form. It's really, to see this is a really classical thing. So now the question is to find the differential identities of a given algebra. That means find a basis of the ideal of the differential identities by means of the a basis as a TL ideal. This is not a really easy task. Sometimes it's harder, it's even harder than the ordinary case. Sometimes it's easier, and this is depend on the action on the Lie algebra. Okay, it's really strictly related to the structure of the Lie algebra that is acting. For example, Professor Gianbruno and I, in 2019, we determined the generators of the T ideal of UT2 epsilon that are actually the two polynomials I showed you before. Okay. Of course, classical things, we want to define a combinatory approach, so we want to define some invariants. So we consider, in this case, the space of multilinear differential polynomial. Again, since characteristic is 0, then the T ideal of differential identities is completely determined by its multilinear polynomial. And the way to show this is a classical, it's by the multilinearization process. It's really standard. And then we can consider then the codimension, the differential codimension as the dimension of this quotient. Okay, that okay. Then this then differential codimension are actually an invariant that gives us information also on the growth of the actually on the co-growth, but on the growth of the differential codimension of our L algebra A. An example, again, in the same paper with Professor Gianbruno, we determine the codimension sequence for UT2 epsilon. That is this one. Okay, so now let's fix the notation in the ordinary case. That is actually what Professor Plowman in the first talk introduced. So I'm we are going to consider, if we consider an ordinary associative F algebra, we know we have all the theory of polynomial identities. In particular, an example, Maltsev in 1971 determined, for example, the T-ideal of UT2 that is generated actually as T-ideal by this polynomial, the product of two commutators. Now, a classical problem in PI theory is, since we cannot determine the codimension sequence actually for the most of the algebras, then since the codimension sequence tell us information about the growth, then a really classical question is to try to study it at least asymptotically. If A is a PI algebra, so is an algebra that satisfies non-trivial polynomial identities, then Regev in 1972 actually proved that this codimension sequence is actually exponentially bounded. And Kemmer also proved something more, that is that the codimension sequence is exponentially bounded or grows polynomially. So there are no intermediate growth. And this is really was really a breakthrough. And in this contest, Amixur conjectured that for any PI algebra, actually there exists this limit, and is actually a non-negative integer. Gianbruno and Zaitsev, they give a positive answer of this conjecture in case of associative algebras, and they call this limit the exponent, PI exponent of A. An example of exponent is the exponent of UT2 is actually equal to 2. So now the question, I think another things, when they prove this result, they give actually an actual way to compute it that is connected actually to the description, the algebra structure of the algebraic considered. What I mean, let's put our us in a simple case. So A is a finite dimensional F algebra. I consider F algebraically closed, but we know the codimension sequence doesn't change by extending the field. So it doesn't really matter for codimension that F is algebraically closed. And then we consider the Jacobson radical of A. Then we know there exists the well-known Wedderburn-Masseff decomposition that tell us that there exists a maximal semisimple subalgebra B of A, such that A can be written as a sum of B and the radical Jacobson radical. Also, we know that B can be also decomposed. B, a semisimple associative algebra, can be decomposed in a direct sum of simple algebras. Then Gianbruno and Zaitsev, they actually proved that the exponent is the maximal dimension of this subalgebra of A, where BI, BI2, BIR are basically the simple component of B, sum of the simple component of B, all distinct, such that they satisfy this rule. So this product is not zero, okay? So we have an element of a simple component, an element of the radical, and so on. It's not zero. So now the question is, we want to stand this the exponent. We want to see if the exponent exists for differential identities, okay? And the problem is that, as we can see here, it's really important the existence of the Wedderburn-Masseff decomposition. So the first question is, what we can say about the Wedderburn-Masseff decomposition for L algebra? So first of all, I'm going to introduce you a definition that if we have any subset of A, it can be a subalgebra, can be an ideal, can be whatever, we call it L invariant if basically S-L is the set, is this set, where is it? Is the images of element of S through element of the basis of universal enveloping algebra is inside S. So if this is satisfied, we call as L invariant. So a really interesting theorem of Hochschild tells us the Jacobson radical of any associative algebra is always L invariant. So if I apply derivation on or composition of derivation to the radical of my algebra, then I get again an element of the radical. The question now is, okay, let's consider the weatherbone mass decomposition. Then does a maximal semisimple subalgebra of A that is L invariant always exist? So we are asking, if there exists a maximal semisimple subalgebra, they are L invariant. So the answer is depend. If L is a semisimple Lie algebra, then the answer is always positive. So there always exists a maximal semisimple subalgebra that is L invariant. And this is a theorem of Gordenko and Kochet of 2014. If L is not semisimple, the answer is negative, in the meaning can exist as, or it might happen that for every maximal semisimple subalgebra, then this subalgebra is not L invariant. In fact, we have an example that if we consider it as UT2 with the action of the derivation, one-dimensional Lie algebra generated by the derivation delta. Sorry, here it's a misprint, is delta. So it's the derivation induced by E12. Then maybe since I lose a bit time in the beginning, I'm gonna skip this because it's all the demonstration of this. I'm gonna skip. I'm gonna give you just the final result. Then for any maximal semisimple subalgebra we take, so if we consider any weatherbone mass decomposition, then B is not L invariant. So B basically is sent, actually it's sent to a linear combination of element. It's actually sent to the radical, okay? So it's not invariant, is the composition, in the meaning that B is not invariant. Okay, so we have a problem. As we know, in the theorem of Jambrun and Zaitsev, when they proved the existence of the exponents, we have that we need a weatherbone mass decomposition, and in our case, we need a weatherbone mass decomposition that is L invariant, but we don't have this. However, Gordienko in 2013 proved that if A is a finite dimensional algebra, he actually proved this in a way more general, in a more general cases. In fact, we have with action of algebra. Okay, so it's more general. Actually, is the result, but adapted in our case, Gordienko proved that if A is a finite dimensional algebra, then actually the limit, this limit, exists and is a non-negative integer, and we call it L exponent of A. And these are actually two examples of the exponent. We have the exponent of UT2 epsilon is 2, and again the exponent of UT2 delta is 2, and they are actually equal to the exponent of UT2 in the ordinary case. Okay. But so the question now is, okay, we have this exponent, but how he reached this result, since we don't have an L invariant weatherbone mass decomposition? He had to take a really, he took a slightly different strategy. In fact, since we consider our L algebra A and its weatherbone mass decomposition in the sense of ordinary case. So this might not be L invariant. So maybe B is not sent by derivation inside B. Then we can, however, consider the canonical projection of A to A quotient J, to this quotient space, to this quotient algebra. And of course, since J is always L invariant, this new algebra bar A over line A is a semi-simple L algebra. So we consider its decomposition in L semi-simple algebras. And then we consider the pre-images of this decomposition, okay? And we call it AIL. Then Gordienko proved that the exponent is the maximal dimension of this subalgebra of A over line A, bar A, where these are the simple components, okay? Some of the simple components, and they are all distinct, and that satisfy this property. So this product must be not zero. Be careful. This one is really a more complicated action, and it's because we have to take in consideration that where the bone mass of decomposition is not L invariant. So we have these two different. It's how can I say? It's a different way of computing the exponent of objects that they don't have an invariant weatherball massive decomposition. Now, what we know? We know something more. We know that if we consider the ordinary exponents and the L exponents, we want to try to compare them, right? Because in general, we know that the codimension, the ordinary codimension, are less or equal to the differential codimension. This is really standard because the space of multilinear polynomial, ordinary one, can be embedded in the space of multilinear differential polynomial, and this is always true. And in particular, this tells us that the ordinary exponent is always less or equal to the differential exponent, the L exponent. In a paper of 2014, actually Gordienko and Kochetov conjectured that for any finite dimensional L algebra A, then we have actually that the L exponent and the ordinary exponent are equal. This is quite can appear quite strange because we know when we consider algebra with the, I don't know, graded algebras, algebra with involution, this is not true. This is not true. We have example that this is not true, that the exponent, for example, with involution, it's greater than the ordinary exponent. However, they conjectured this, and they actually, in the same paper, proved that this is true for L semi-simple Lie algebra. So when L is a semi-simple Lie algebra, this is true. And this can be, it's kind of, we can kind of expect it. Why? Because for L semi-simple, the weather massive decomposition always exists and is L invariant. So it's not that surprising in some way. In a paper of 2022 with Dos Santos and Vieira, we proved that actually if we consider any Lie algebra, so not just semi-simple, then the differential exponent is 1 if and only if the ordinary exponent is 1. So for 1 is true. So for polynomial growth, it's true. Then in a paper that is just being published now, I proved that actually this conjecture is true for any Lie algebra L. And the reason is because of the structure of the action. So we have a really strong action that is by derivation, and the derivation satisfy the Leibniz rule. So one really key thing in my proof was the fact that we have the Leibniz rule. The other key thing is that any L simple algebra, so our simple L algebra, it's actually just a simple algebra. So it's just matrices with action of derivation. These two things combined give us the positive answer to the conjecture of Gordienko and Kochetov. Do I have more time? Maybe 2 minutes? Yes. Okay. What time is it? I think yes. So a consequence of this result is we have a really nice consequence of this result, that is about the growth of the variety. In fact, if I consider a variety of L algebra, so it's a set of algebra that satisfy the differential identities of our algebra A, then as classical result, we know in the ordinary case, we can define the polynomial growth that V as polynomial growth if the codimension sequence of I is polynomially bounded, and we say that varieties as our variety V has almost polynomial growth if the codimension sequence is not polynomially bounded, so grows exponentially, but every proper subvariety has polynomial growth. Of course, if L acts trivially, we have the ordinary variety of algebras. For ordinary variety of algebras, Kemmer proved that the variety generated by UT2 has almost polynomial growth. And with Professor Gianbruno in 2019, we proved that actually UT2 epsilon, the variety generated by this algebra, has almost polynomial growth. However, not if we define any action on UT2, by derivation, this not necessarily as almost polynomial growth. The variety generated by UT2 with this general action has no almost polynomial growth. In fact, if, for example, we consider UT2 with delta is the derivation induced by E12, then the variety generated by this algebra has not almost polynomial growth. However, we have that in case L is a solvable Lie algebra, is a really a condition that's we have to impose is really necessary and important, then UT2 and UT2 epsilon are the only finite dimensional L algebra generated varieties, L varieties of almost polynomial growth. And this is, of course, come from that classification of L variety of polynomial growth, that this comes from the fact that the differential exponent, the L exponent, and the ordinary exponent are equal. And then, in case L is solvable, then we have also this more equivalent condition. Thank you.
Okay, thanks. I see that there are some questions. Okay, let me start. I don't know, maybe I can see, maybe Wesley. No, I don't see questions or comments. Oh, yes.
Well, I have one question. So my question is the following one. It turns out, it's about key definition of these identities, yes, differential identities. So we start with Lie algebra of derivations, yes, and we choose some bases, but we can choose different bases, yes, and then we, essentially speaking, will obtain different differential identities for one and the same algebra.
Yeah, formally are different, but they belong to all, they can be generators one from the other. So when you fix a basis, all the other, if you change basis, you can write the new identities as a linear combination of the one in the previous basis. So they are all in the T ideal. You change.
So this statement is quite trivial, or it was proven somewhere?
Yeah, it's quite trivial. It's because it's like this, because a basis is the derivation of a linear combination of the one in the basis, right? And and then if you imagine you have as exponents in your variable derivation in the new basis, you can always write this new derivation as a linear combination of the previous basis. And this manipulating, you obtain the relation from passing through the derivation, the differential identities in the new basis through the and the previous basis. It's basically a changing of basis. in the exponent.
Well, in multilinear case, yes, it seems obvious, but
Yes.
you normally work in characteristic 0, yes?
Yes. In characteristic
So,
0, yes.
Okay, then another question. Okay, so we have derivations, but we also have a lot of generalizations of derivations, like a lot of them. Have you ever thought to try maybe somebody else to do the same stuff, but not with derivation, let's say with delta derivations? There are a lot of them. I'm not gonna even enumerate them.
Okay, I never, so far I haven't studied them. I didn't approach them, but they might be interesting. I don't know. We have to see.
Yeah, there are a lot of people who study different kind of generalization of derivations, and over these derivations you can also introduce structure. In many cases of Lie algebra, sometimes Jordan algebra, sometimes something else, and so a lot of people are doing it. So it could be
Can be
another generalization.
Can be an interesting for new papers. It might be interesting. Yes.
Yes. Okay. Thank you.
Thank you. Thank you.
And we also got questions here. Yes, thank you. We also got questions here. We are in the...
Sorry. Okay, maybe there is another question.
Of Rio Grande do Norte. And we just gonna have some patience because we need to share the sound and the microphone. This is the question from the audience. So, can we start?
Yeah, I am in here.
Go ahead.
Carla, thank you by your presentation. I have a question. Is there some classification for the derivation of the Grassmann algebra?
No, there is no classification for the derivation of Grassmann algebra. I mean, there are some results about the finite dimensional Grassmann algebra. So if you take just an element, and then there is. But in general, for an infinite dimensional Grassmann algebra, there is no classification as far as I'm aware of the derivation of the Grassmann algebra. In fact, I studied the Grassmann algebra with derivation, the differential identities, in a paper, but just considering the inner derivation, because it's still an open problem to understand which are the not inner derivations, so the external one.
So thank you.
Thank you.
Thank you.